All right, good morning. Let's get started. So last time we introduced the notion of gain. We need to introduce the notion that we need to have some form of amplification, right? The output from a microphone that's microvolts, it's just not going to drive a speaker. And then in order to get that gain, we found that there is a component, how is it called? A component that we can use for amplifiers in circuits. It's called operational amplifier, or for short, op-amp. Op-amp, right? And this op-amp component we can use. It's somehow made, it's very interesting how it's made and so on. You learned that in EE 140, should you take that course. But anyways, this operational amplifier is very convenient to build all sorts of amplifiers. It has one very strange property, and that is the gain is extremely high. In fact, it's almost infinite. For all practical purposes, in most circuits, you can assume that the gain of an operational amplifier is infinite. And of course, infinite gain, well, I mean, large gain is nice, but infinite gain is totally useless. So then we've also found out that the combination of very high gain plus something that called feedback, this combination allows us to set a very precise gain that is not infinite, but has some appropriate value, like 10 or 5 or whatever we need in a particular circuit. Okay? And we said that this feedback, this idea of feedback, is a very common concept that's used all over engineering. Really, lots of you couldn't. Airplanes, cars, and so on, they use lots of feedback loops to control how the engine works, to control that the airplane doesn't, you know, does it flies nicely, a helicopter even more, and so on. They all these systems, they use feedback, also a heating system, right, to keep the temperature just at the right level. It figures out what is the temperature. Well, if it's too cool, it turns on the heater. And if it's still too cool, it turns on the heater more. If it's too warm, maybe it turns on the air conditioner. So all of these are examples for feedback systems. They're very important, used very much in electronics, and most likely you're going to see feedback in other classes also. And so we don't need to cover feedback in any very great depth here, but we'll just say enough so that you can also make the connection between the different stories about feedback that you hear in other classes also. So here is feedback theory light. So just 2 slides on feedback. So the first thing that we should say is, well, what really do we mean by feedback? Well, very, very loosely, what we mean is that here we have an output, here we have an input, and we take some of the output and we feed it back to the input. Okay? That's what we mean with feedback. If you find a circuit that has somewhere an output, somewhere else it's got an input, and you find a connection that goes from the output of the circuit around and sticks right back into the input, well, you probably have a feedback network there. Okay? And so whenever you see in a circuit diagram, whenever you see one of these triangles, oops, that's an op-amp, look for the feedback loop. The second thing to look for is the feedback can go to either this terminal, it can go to this terminal, right? It can go to the plus terminal, or it can go to the minus terminal. Now, conveniently, this is called negative feedback, and this is called positive feedback. Almost always, we are going to use negative feedback. Almost always. I'll show you at the very end an example, or end of today's lecture, an example where you actually use positive feedback. But almost always, we want to use negative feedback. Okay? And again, when you dive deeper into feedback theory in one or the other classes, you will understand why that is and how we ensure that the feedback is negative. Here in EE40, unless it's very obvious, I make a connection back to the positive terminal. I tell you, hey, you know, this is positive feedback. So almost always, it's going to be negative feedback. So negative feedback. Now come 2 pieces of nomenclature. This component here is an amplifier, right? Specifically, an operational amplifier. It's got a gain. What is the gain? Infinite, right? But this whole thing here is also an amplifier. It's also got an input, Vi. It's got an output V out, and it's got a gain that is V out over Vi, and the value, well, depends on all the stuff here, on this one and on this one, and it usually is not infinite, right? I mean, better not, otherwise we would have a useless circuit. So that this gain from here to here, that includes the feedback loop, which is closed, is called the closed loop gain, okay? So there is this gain from here to here. That includes everything, not just the op-amp, but also this feedback network that in electronics, of course, is going to be a bunch of resistors or some other electronic components. Right? This whole thing is called the closed loop gain, and it's V out over Vi, and we call it usually capital AV. Of course, we can give it any name that we want, but it's very common to give it the capital name. And then there is also the open loop gain. That's the gain of just this box here without feedback around it. So that would be the difference of these two voltages amplified. And so that's the gain AV. That's V out, this V out, which happens to be the same here as the overall V out, right? Divided by the difference of these two voltages, these two, right? That is the little AV, and it's infinite, right? So that's called the open loop gain, and it's of course not the same as the closed loop gain, okay? Remember that, it's very simple, it's simply nomenclature, but remember that because if, for example, you use this nomenclature, capitalization matters, right? Of course, we could also call this XV and then it wouldn't matter, but then it would be different, but this is sort of common, yes? Why we prefer negative feedback? Could I defer this for a little bit later? We will see that for this circuit to act as an amplifier, we need to have negative feedback. Okay? We will see later that if we have positive feedback, it does something totally different that is also useful in some situation, but it's not an amplifier. Okay? So that's why usually, very much most of the time, we will have negative feedback. Yes?
So when you say open loop, it means like there is no feedback? Exactly, right? If we had this box and we didn't have this thing here, then there would be no loop. That's the same as I had taken a scissor and I cut the loop and opened it, right? Then that's open loop, yes. When it's closed, then there is no V of input into the negative side, right?
If it's closed, well, there are, of course, voltages here, right? There is a Vi plus, which in this case happens to be Vi, and there is a Vi minus, which in this circuit happens to be also equal to Vf, right? Right? These voltages exist and they have some values and we can calculate them and so on, but they're different than if we had the feedback loop not present, right? Obviously, if we introduce this box, it's going to somehow affect what that voltage Vf is. Yes?
So the lowercase ab is equal to infinity.
Yes. This one.
Yeah.
Okay.
Does that mean that since Vi must just be a finite value, that the negative feedback has the value of negative infinite voltage?
Okay, we'll just get to this, right? It's kind of funny if we have an infinite gain, how do we avoid having infinite voltages in our circuit? And we'll get to that in just a second. That's a very good observation. Something's fishy here, right? Yeah. Okay, any more questions about that? Yes.
So for an ideal amplifier, Vi plus equals Vi minus.
Okay, yes. So that's again. That gets to this question. Well, if this is infinite, what do these voltages have to be, and so on? You're right. What you said just is correct. I just want to say it again with a different slide that is just for that purpose. Okay, we're actually even going to calculate it. But you have seen that in the book, and you may also from intuition say, hey, these voltages have to be correct. Your intuition is correct. Okay? All right, so the main things to take away from here is that op-amps have infinite gain. That's the open loop gain. And then we use feedback, usually negative feedback, to produce a closed loop gain from here to here that is different and has a useful value like 2 or 10 or -5. And those two gains are different. So there is an open loop and a closed loop gain, and those two are different. And this slide hopefully gives the definition of them. And if you still get confused about it, come and ask us. Okay? All right, so now let's do a little bit of an analysis here. So the voltage here is V out. I just repeat that. Let's arbitrarily give the voltage here the name VF. And then this box here, we will just look at in a moment how to build it. But this box, what it really does is it produces VF as a function of V out. VF is some factor F times V out. Okay? So we could implement the box with the voltage divider, and we'll do that later. But this slide is more general, right? That's sort of the feedback theory, the sort of mathematical description of what's going on. Okay? Now just the operation amplifier itself basically says that V out is equal to AV. That's the open loop gain. That's just what this box does, times whatever is at its input terminal. So we call these voltages VI plus and VI minus, and they happened also to be here EVI minus VF, right? So that's always true. This expression, of course, is always true, that whatever the voltage is at the output of the operation amplifier, that V out is equal to AV times the difference at its two terminals. Okay? All right? So we just wrote down the definition of the op-amp. That's this equation here. Okay? So then we also know what is VF. VF is equal to F times V out. We just had written that up here before, right? Okay? And now it's purely mass, right? Of course, now we have the unknown, the output voltage in this equation. We can solve for that. We can solve for V out times 1 plus F is equal to VI times AV. We can divide by 1 plus F, and we also F I think times AV. Look at this. Okay, we can divide by this 1 plus F times AV term and also by VI, and then we get this result down here. Okay? So we wrote down two equations that simply describe circuits. And once we have written down these equations, we can solve them using purely mass, and that's what we get. Okay, so actually, what is this? This here, is this the open loop gain or is it the closed loop gain of the circuit? That's the closed loop gain, so that would be using the nomenclature from the previous slide, would be capital AV. And it's different than little AV. Okay? So now, what does this equation tell us? Well, we've said that AV in practice is going to be very large. In fact, infinite if the operation amp is good, right? Or ideal, right? So then we could divide by AV to calculate what is V out over VI. Well, we can divide by AV, then we get 1 over AV plus F. Well, if AV is infinite, this term drops out, right? 1 over AV is 0. And consequently, this closed loop gain of our entire circuit now is 1 over F. Let's think about that a moment, right? We have a gain that ideally is infinite. In practice, it is just large. It could be 1 million, it could be 100,000, it could be maybe even 10 million in some operation amplifiers. We don't even know the exact value of this. What about the closed loop gain? It depends only on this factor F. So if we somehow can produce that factor F, for example, using a voltage divider, that has a very precise and definite value, then the overall closed loop gain has a very precise and definite value, regardless of this term varying a little bit. Right? Okay. Very remarkable, right? So this feedback trick helps us apparently to turn something that does the right thing. It has gain, but it's very imprecise. To turn that thing into something that still has gain, but now it's very precise. Because the precision is set by something else that we can control accurately. Okay? So that's one of the really wonderful things about feedback, that we can separate the machine that provides all the power. That's this little AV, right? The operation amplifier. We can separate that from the control of how much power we actually apply. Okay? Okay? And so that is the fundamental, wonderful advantage of feedback that we use over and over. Okay, so that was feedback theory light. I hope that helps you to connect the dots. If you hear about feedback in another class, it's the same thing. And hopefully, whatever you learn there, you can use it in 40, and whatever you learn in 40, you can use it in that other class. Okay, so now we go back to real circuits, right? What does it mean? We go back to real circuits. Well, this box here, just F, was a very mathematical concept. Here in practice, we will have to build a circuit for that, and the simplest thing we already said is is a voltage divider, right? So we can take the voltage V out here, and we can produce the voltage VF using this voltage divider. Now again, that's something which by now probably you can write right away. You can write VF is equal to V out times R2 over R1 plus R2, okay? And therefore F, which is equal to Vf over V out, is equal to R1 plus R2 over R2, or, well, 1 over F, which is equal to AV, what's that? That's the closed loop gain, right? That's V out over Vi, okay? That's 1 over F, and that apparently is equal to 1 plus R2 over R1, okay? So what before we had derived using this ideal feedback theory, right? We had using feedback theory, using math, basically we found that in such a feedback circuit, go away. We had found for any circuit like this, AV is defined as V out over Vi is equal to 1 over F. We have used that now. We've implemented this F with the voltage divider, and we found that then for this circuit, the gain happens to be 1 plus R2 over R1. Again, what we said before, even though the operation amplifier's gain, we don't even know the exact value, right? Remember that data sheet was all over the place. Sometimes it's 200,000, on a bad day it's only 20 or 30,000, right? But because it's large and we use feedback, then the gain, the closed loop gain, is set by just resistors. Wonderful. Yes? Yes, of course, yes. Thank you. Yeah, have to somehow help yourselves out of the problem, right? Okay, so now let's get to the question that somebody here asked. Well, something's fishy here, right? We have a gain of infinite, so if, for example, we had 1 millivolt at the input of our operation amplifier, what would the output voltage be? Infinite, right? And apparently it's not infinite, because if the overall gain of the circuit is maybe 2 or so, well, we put the volt in, we get 2 volts out, for example. So what's going on here? Well, we'll first do a little bit of math, and then we will try to intuitively figure out what the math actually tells us, and then we say, well, silly, why did we even do the math? Okay? So let's look at this voltage here. Let's calculate it, what it is. Okay? What is this voltage actually conceptually? Well, it's the difference of the voltages at the 2 terminals at the input of our operation amplifier, right? Okay. So what is that difference? Let's calculate that. So this voltage Vx is equal to the voltage here, well, that happens to be Vi, minus the voltage here, well, that happens to be Vf. And so that is equal to Vi minus F, and F happens to be R2 over R1 plus R2 times times V out, and V out is AV times Vx, right? This thing here is nothing but V out, right? Okay? So this is purely sort of mathematical, right? And again, F in this circuit happens to be R2 over R1 plus R2. I just used that convenient nomenclature that I had introduced before. So now we can again solve this thing, and what we get is Vx over Vi is equal to 1 over 1 plus F times AV. Okay? Okay, so let's look at that. Well, what is F times AV? Very big. In fact, if the operation amplifier is ideal, then this lowercase AV is infinite, and therefore F, which is maybe 0.1 or whatever, right? F times AV is still infinite. And consequently, this whole thing is 0. Okay, so what have we just found out? Well, the voltage at the input of the operation amplifier, the voltage difference between the 2 terminals of the operation amplifier is 0, right? It's 0. That voltage Vx between the 2 terminals is 0, or the 2 voltages at the positive and negative terminal of the operation amplifier are the same, just as you said. Okay? Now, there are various things we can sort of interpret into this thing. First of all, if the operational amplifier has a gain of infinity, it just has to be there, right? It has to be that way. If we had only 1 microvolt at the input of the operation amplifier and its gain really is infinite, what would the output voltage be? Well, it would be infinite, right? And so, because that's not the case, V out is not infinite, that would be useless, right? That can't be. So the only way we can get, with an ideal operation amplifier, we can get a finite voltage at the output, is that this voltage Vx at the input of the operation amplifier has to be 0. Then we have 0 times infinity, and what's the result of 0 times infinity? That happens to be V out, right? We cannot really tell what is 0 times infinity. It depends on something else, and we have calculated that using this closed loop analysis. Okay, 0 times infinity, mathematically it's undefined, it's not infinite, it's not 0, it can be anything. Okay, and in this case it happens to be just V out. Okay, so that's just sort of the mathematical thing. Now in practice, of course, the gain of the operation amplifier is not infinite. It's maybe a million. So then, for example, if we had at the output, if V out is 1 volt, what would be Vx? 1 microvolt, right? So in practice, this voltage Vx is going to be a very small voltage, like 1 microvolt or so, right? Now, in some cases, when we build an extremely high precision circuit and so, maybe it matters. most of the time, this 1 microvolt is as good as 0. And consequently, if we assume that our operation amplifier is ideal, then we can also assume that Vx is 0, and our calculations get a lot easier. And that's what we're going to see now. Okay? So the thing to... Now, if you understood all of this derivation and so on, that is really great, and I would like that you understand all of it. But if you didn't quite understand it and so on, then I very strongly recommend that you absolutely remember this. If we have negative feedback and our amplifier is really high gain, like infinite, then this voltage Vx is 0. In fact, not approximate, then it's exactly 0. Okay? And we're going to use that over and over and over again, and our analysis of op-amp circuits is going to get almost trivial if we use this, and it's a laborious chore if we don't use this. Okay, so we've calculated the gain of this thing before, but before we sort of calculate complicated way by letting go AV to infinity and so on, all these Limes calculations, so right? Now we can do this much more easily by knowing that Vx is equal to 0, yes?
I know that the actual difference between the positive and negative pole curve is 0. Because if you have a voltage source at Vx, then it won't be 0 anymore, right?
Yes. Then you have violated this condition that you have negative feedback. Okay? If you put the voltage source in between there, then of course the voltage here is pinned by that voltage source. No longer, the operation amplifier and the feedback loop can no longer say, I'm going to set this voltage such that the difference Vx is 0, right? So don't put a voltage source there. If you do, then the negative feedback loop's broken, and then this analysis doesn't apply anymore, and you probably have built something that in most cases is not very interesting. Okay, so that would probably fall into the trick category question on the exam, if I would stuck a voltage source there. Maybe I'll do that in 2 or 3 weeks, but not now. I don't want to confuse it just yet. Maybe you're already confused, right? So that's enough. Let's get that confusion out of the way. But anyways, so I hope you're not confused, but even if you are, the thing to remember is that this Vx is 0, because we have a negative feedback loop, okay? And the operation amplifier is perfect anyways, is ideal, okay? So, now, if this voltage is 0 and the voltage here is Vi, then what is the voltage Vf? Vf is equal to Vi, right? There is no difference in between Vi and Vf. Well, then they are the same, right? So why are they the same? Well, it's because we have this negative feedback loop, right? There is no wire or so that sets that. No, it's the operation amplifier together with the negative feedback that somehow managed to do it that way. And the math tells us that it does it that way. Okay? So if they are equal, then we can still use our voltage divider equation. We still can, of course, write Vf is equal to Vout times R2 over R1 plus R2. And now we just had said that Vf is also equal to Vi. And now, of course, we can solve this easily for Vout over Vi, which we also call the closed loop gain. And that is equal to, well, we just have to take the inverse, right? R1 plus R2 over R2. Done. Okay, by knowing this, we managed to solve this problem trivially and very, very quickly. Remember this, right? When you solve for voltages in op-amp circuits, remember, look, is there a negative feedback loop? Yes. Well, in that case, Vx. Find out where Vx is in your circuit, right? Vx is 0. Use that in analyzing the circuit. We'll do now a bunch of examples of this. Okay? Okay, yeah, here is another example. So again, we have an operation amplifier. Do we have a feedback loop? Yes. Where is the feedback loop? Well, here is the output. Here it goes back to the input. That's our feedback loop, right? Well, so there are two kinds of feedback, right? There is positive feedback and there is negative feedback. Well, which one do we have? It's negative feedback because here we have the minus sign. Okay, perfect. So we have negative feedback. We have an ideal operation amplifier in all the assignments and everything. And so the operation amplifier is always ideal, except when I tell you, hey, it's not ideal, it's something else, right? So here it's ideal. Okay, so then, do we have a voltage Vx somewhere? Okay, Vx. And that is 0 volts because we have negative feedback, right? So now, how could we figure out the output voltage? Well, let's put a common node here. This voltage here is 0. Then what's the voltage here at the minus terminal of the op-amp? This voltage has to be 0, right? Okay. So why is it 0? Well, we figured it out using some math. Now we just know it, right? Don't worry about it anymore. We've checked its negative feedback. Consequently, it's going to be 0. Okay? So Vx is 0, and in this case, because on the positive terminal we have 0, well then on the negative terminal we have also 0 volts. Okay, so now what is the voltage here? This voltage here that I just indicated. This is V0, right? Because here we have a voltage V0, here we have voltage 0 volts. Well, the difference, V0 minus 0 volts, just happens to be V0. Now, if somehow, of course we don't know what V0 is, right? That's just the whole point. We want to figure it out. But if somehow we would know the current I2 flowing through resistor R2, then, of course, we could use Ohm's law, and we could figure out from the current. Yes, I think you get it, right? We could figure out what that voltage V0 is. So how do we figure out what that current I2 is? Any ideas? Which one? Yes. Yes, yeah. Okay, all right. So let's see, what do we know? Well, we know Vi, of course, right? We want to know what V out is for a given Vi. We know R1. Well, do we know the voltage across the resistor R1? That's Vi. Well, do we know the current I1 flowing through the resistor R1? Well, of course, we know that. It's equal to Vi over R1. Okay? So now we have one more thing. Here we have a node. We can apply KCL to this node, right? We have into that node, we have flowing current I1, so that's minus I1. Out of the node is flowing current I2. And what current is flowing into the operation amplifier? 0, right? So I2 is equal to I1. Okay? So now we can find out, using Ohm's law, we can find out that V out is equal to R2 times I2, which is equal to I1. And now, R2. And now I've made actually a small mistake here. What is the mistake that I made? There is a minus sign here. Why is there a minus sign here? Look at this. The current goes from the minus sign to the plus sign through the resistor R2. Then Ohm's law has a minus sign. Okay, so sometimes it happens. I drew these voltages and currents with arbitrary signs. Like I tell you, don't worry about it. Just draw them and calculate the right thing. But then, when we apply Ohm's law, well, we have to be consistent. Say, heck, we chose directions that go in opposite ways, and therefore you have to use a minus sign on Ohm's law. Okay, so now we have minus R2 times I1 is equal to Vi over R1, and we can solve for V out over Vi, and this happens to be, is this the open loop or the closed loop gain? That's the closed loop gain, therefore a capital AV is equal to minus R2 over R1. Okay? So very, very simple calculation. Just knowing this business about Vx, that is 0, we can solve such a circuit very easily, yes. Why are they equal? Well, because we have this KCL equation here, right? We have a current flowing into that node. That's the current minus I1. Because I always sum up currents that leave the node, so I have to put that minus sign. Then we have the current I2 that is flowing out of the node, so that's this thing. And finally, we have no current flowing into the op-amp, therefore the currents must be equal. Because that's how op-amps are made. Okay, so it's a bloody miracle, and we will talk a little bit about that. It's a property of transistors. It's like a switch, right? A voltage switch, light switch. You can control a lot of current flowing through the light switch, but there is no current, hopefully, flowing out of your hand into the light switch. Transistors can do the same thing, and much better even, and there is no current flowing, even though they control the current that's flowing. So there is a transistor inside that does this. Bloody miracle. Billion times in a computer all the time. Amazing. Okay? All right, so now basically you know everything. Some of you look a little bit more assuring that, yes, of course, I know it. Leave me in peace with this stuff now. And for some of you, well, it's maybe not totally clear yet. So I actually have now a bunch of examples, and we'll go over these examples. Okay? So hopefully that will help us. All right, so again, we want to figure out what is, well, in this case, the output's a voltage, V out, and the input happens to be a current. Hey, you know, we also can have an amplifier that takes at the input one thing and at the output something else, right? If there was a, if this was a light switch, we put a little bit of mechanical energy in, and then we get a lot of electrical energy out, right? So in this particular case, the input happens to be a current, the output happens to be a voltage, well then the ratio, of course, is a resistance. This is not a physical resistor, but this whole circuit synthesizes a resistor, and we call that resistor Rx. Okay? Can do that. All right. So now we want to analyze the circuit in order to figure out the value of this Rx. What's the first thing we're going to do? Okay, you're jumping a little bit ahead, but you're almost right? But really what we're going to do, in a blink of a second, we're going to say, hey, there is a feedback loop. It's negative feedback because we go back to this minus terminal here. That's really the thing that we have to verify. You have to do that. Not in the next week or so yet, but maybe by the time we are at the midterm, I could try to make a triage. Those who really understand circuits, they go and make this observation. See, oops, he pulled one on us. He put the positive feedback, and I need to use a different theory to analyze it. Okay? So in general, you have to make sure that it's negative feedback. Most of the time it is. So you will still get an A minus, but if you want an A plus in the course, you need to do this check, because here and there may be a situation where it's not the case. Just like in real life. Sometimes it's not negative feedback. Here it is, all right? So we have that. So now what's the next step? Now comes sort of the fun part, the real solving the problem. Yeah, we can do KCL at this node here. What's the current here? IS. What's the current here? 0. What's the current here? IS, right? And then we can, of course, write again the voltage from here to here. Well, what is this voltage here? 0 volts, right? Therefore, what is the, let's make this a ground. So this is 0 volts. Then what's the voltage at the node where it's 0 volts, right? Consequently, this voltage here is V out minus 0. That just happens to be V out also. The voltage across the resistor. And then we again have this funny Ohm's law with minus signs, so Rx is actually equal to Rf. Turns out this is a very important circuit because, for example, if you pull, when you make a phone call to Europe, what happens to the bit? What happens? Is it from your cell phone the RF signal goes all the way to Europe? Nah, doesn't do that, right? You will have to bring a pretty damn big cell phone along with a huge power amplifier and have a huge antenna that would be bigger than an umbrella. It doesn't go. Right? Well, that would be another little problem, right? No, what it actually goes through a fiber, right? It goes. It's collected at the cell phone tower, and there it's turned into an electrical signal. Then it goes maybe to the central switch or somewhere, and there it's turned into an optical signal. How is it turned into light? Using a laser, right? Again, using electronics driving that laser. Now it's light, and it goes through a fiber optic cable, which is basically like a piece of glass, but it's super transparent glass. It's really transparent glass, and it goes on the bottom of the ocean all the way to Europe, somewhere in France or in Great Britain. They tie into it, they turn back all that light back into electrons using a circuit that is just like this one. This little piece there, that's a photodetector. Have you ever seen one? Where? In Lab 1, right? In Lab 1 you had some kind of a photodetector. I use better photodetectors there so that it goes at, whatever is it, 10 gigabits per second or so. And you didn't go quite that fast in Lab 1, right? But, okay, so we just analyzed a very useful circuit. So here we have another example. So this one we're going to solve a little bit differently. So let's first do as if the part that I circle here was not present, okay? Let's do as if that part wasn't present. So we only have resistor R1 and RF, and then we have the input VI1. So could we find out what is V out over VI1? Actually, have we seen that circuit before? Well, of course, it was just, was it this one here? I messed it up a little bit, right? Okay, so that's what it is. So now if we remember the result, then the result was actually R1 over RF. And if we don't remember it, oh! Okay, yeah, so if we look it up, then we at least have to look it up correctly, not like me, right? So can look it up or we can calculate it again. All right, so now, of course, the stuff that I circled in yellow is actually there, right? And so how could we figure out what the total output is if we have not only VI1, but also VI2 and VI3? Is there a nice trick that you might remember on how to deal with that? Yeah, superposition, right? We really need to calculate. We can now do as if everything was gone except for, let's say, VI3, and then we would get V out over VI3 equals minus RF over R3. Right? And then, of course, we can finally do the same thing again. We get V out over VI1 is equal to minus RF over R2. Okay. And then finally, how are we going to figure out what V out is when we have all the inputs? Just add it together, right? So this is equal to V out is equal to minus or F times Vi1 over R1 plus Vi2 over R2 plus Vi3 over R3 done. Okay? So, all these tricks that we learned before, like superposition, very often it's very convenient to apply these tricks to op-amp circuits because very often we have multiple inputs. In fact, what does this thing do? It's kind of a sort of a it's like a Swiss pocket knife, I think that's the thing. Right? It does amplification, right? It amplifies the signal by RF over R2 or RF over R1 and so on. And then it also sums up all the contributions. So it's a summer and an amplifier all in one. Wonderful, huh? So that's how we make inexpensive circuits. We let one component do lots of different things. So we can also do subtraction. A little bit more complicated circuit here. Again, what's the first thing we have to do? Feedback. Is it negative? Yes. Okay? Then, because we have negative feedback, we can say the voltage here is 0 volts, right? So then I conveniently already labeled these. So Vi1 is equal to Vi2, right? All right. So now, what is Vi? Of course, we don't know Vi1 and we don't know Vi2. But could you figure out one of them? Okay. Vi2 is a voltage divider. Well, so Vi2 is equal to Va times R4 over R3 plus R4. Now remember, I told you voltage dividers, we'll use them all the time. If you need to think hard about the voltage divider, then you really need to spend an afternoon or an hour or so thinking it through and once forever. Right? Okay, you have a question?
Yeah, I don't get why Vi1.
Well, if we have negative feedback, then we have this voltage. We can always define a voltage at the input between the two inputs of an operation amplifier, and we call that Vx, right? If we have negative feedback, then the value of this Vx is equal to 0. Okay? Okay? So now, if the difference between Vi1 and Vi2 is equal to 0, what? Well, this is an electronic circuit that's getting too warm. Or something. Or maybe it was my connector. So, okay, it's back. That's actually a funny thing, you know. Making a billion transistors and every single one of them works. It's a little bit hard, but we can do this over and over, right? Intel, they happily sell you another 1,000 of these, or 100, better 1 million, right? But the connector, making a good connector, it's very hard, and it costs a lot of money. So actually, in that phone or whatever you have, you pay $30 for the connectors and the case and that stuff, and then $10 for the electronic circuit, for the 10 billion transistors and so on. Okay. All right. So, but we're back to this voltage Vx is 0, and consequently the voltage Vi1 and Vi2 have to be the same. Now, we could also of course, try to do, now I'm starting to really mess this up, but we could, of course, do a KVL loop.
No, I thought that it was current. I'm sorry.
Yeah, okay. It's okay, they're equal, the two voltages? All right. The voltages are equal, yes. All right, so we have that. Now we still have the other guy here. What's the current I1 flowing into resistor R1? Well, that's the voltage VB minus what is the voltage here at the other side of resistor R1? No, it's not 0. No, not at all. It's VI2, which VI1 actually, yeah. VI1, which happens to be equal to VI2, and then we have to divide by R1, and there now we get current I1. And finally we have the voltage here. That voltage is V out. Is this voltage here V out, the one I just indicated? V out minus VI1, which happens to be, happens to be equal to VI2. So that is equal to minus I1 over R2. Huh? So now we have enough equations. We have a whole bunch of equations here. Is it narrow? Times R2. Okay, so now the rest is math, and I did the math at home, so I didn't make mistakes. Hopefully, V out over VA minus VB is equal to R2 over R1 if we choose R1 over R2 equals R3 over R4. R3 over R4. Okay, so that's one solution. Right? If I make this choice on the resistors, then this is actually a voltage difference amplifier. It amplifies, but it amplifies the difference between VA and VB. So operation amplifiers, they can amplify, they can sum, they can take differences, they can turn currents into voltages. Very universal device, right? All right. So we didn't get, if you look ahead, that's the positive feedback. So we'll get to that on Monday. All right? So far, it's only negative feedback. If you have questions, please come ask us.